Okay, it is the numerical methods applied in the structure analysis again, and I will continue the next times. If we solve generalize the general eigenvalue problems, you will see the equation like this one. And for the structural applications, actually, usually we use the formula like this one. Okay. Also, that's the applications for the structural dynamics problems. And last time I introduced the two different solution methods. We can use the power method. And first we have the inverse iteration. For the inverse iteration method, we will try to get the U1 by the K inverse M. Also, we have the other one, which is the direct iteration. Then the U1 will in N inverse K equals 0. Okay. So we have two different iterations method, and the one is the inverse iteration, the other one is the direct iteration method. And if we compare the solution procedure for the inverse iteration method, we need to calculate the K inverse. For the direct iteration method, we need to calculate the M inverse. But usually the K is more complicated than the M matrix. If we use the lambda mass method, the M matrix will be the diagonal matrix. For the diagonal matrix, it is very easy to calculate the M inverse. But for the K, we need to spend much more efforts to get the K inverse. Okay, but actually in the structural dynamics, most of the time we will choose to use the inverse iteration method instead of the direct iteration method. Even the calculations for the direct iteration method is easier than the inverse iteration method. Okay, why we choose the difficult one? Since if we use the inverse iteration method, we will get the eigenvector and the eigenvalue with the minimum absolute eigenvalue. Okay, so that's the. But if we use the direct iteration method, we will get the maximum absolute eigenvalue. If you learn the structural dynamics, you know there is one method to solve the problems is the model analysis. If we use the model analysis, usually we just choose the number of the consider the mode shapes. Usually they are much less than the number of the dimensions of the problems. And which mode shapes we need to choose? Usually we will choose the mode shapes with the minimum the natural frequency. Since if we analyze the contributions to the response of the structures, you will find those mode shapes corresponding to the to the minimum value, the small of the natural frequency, usually it will contribute more to the final response. Okay. Also, you can understand the natural frequency also related the energy which it requires to trigger the model shapes. So for the model shapes with the minimum value, which also means it takes a minimum energy to trigger these model shapes. So that's probably the reason why most of the time the minimum value of the natural frequency, also the natural frequency is the eigenvalue of the problems will contribute more. Okay, so that's the reason we choose, most of the time we choose the inverse iteration method. Okay, but compared to the Jacobi's method, the Jacobi's method, as long as we got the diagonal matrix, and then we can solve all the eigenvalue and eigenvectors. Okay, we can solve if we use the Jacobi's method or the generalized Jacobi's method, we will make all the off-diagonal elements close to zeros. As long as you finish the solution procedure, you got both A matrix and the B matrix, both of them close to the diagonal matrix, then it is very easy to finish the calculations to get all the eigenvalues and all the eigenvectors. Okay, so that's the Jacobi's method. But if you use the Paul method, okay, you will find only one set of eigenvectors. But if you use the Paul method, no matter you use the inverse iteration method or if you use the direct iteration method, for both methods, you can get only one set of the eigenpair. And if you need the second set, the third set, you still need to do more calculations. Okay, so then I will introduce then usually we need more than one eigenpairs, and then how can we get the second set of the eigenpair? And after we got the first two eigenpairs, then the questions will be how can we get the third set of the eigenpairs? Okay, so the problems can keep on going. So after you solve the first three, then how can we get the fourth one? Okay, so remember the concept, and then you can always get one more eigenpair. Okay, so let's say the problems is the equation like this one. However, for the numerical methods, we will assume both A matrix and the B matrix they are known values. So the users need to input both A and B matrix, and the solution method or the programs developed by the solution methods will try to solve the corresponding eigenvalue and the eigenvector. Okay, so right now we will assume we know the A matrix and the B matrix, and if we use the power method or the inverse iteration method, the inverse iteration method is usually it is the one we choose to solve the problems, and then we can get the first pair. Okay, so we can use the previous solution method, and after the solution procedure, we can get the first eigenpair. So we will assume the lambda 1, the x1 was already solved. Okay, then we can assume an arbitrary initial vector. Okay, so we can assume an arbitrary initial vector. Okay, you just can assign any values to the elements of the U0 vector. It doesn't mean the okay. Remember the U0 vector can always be represented by the combinations of all the eigenvectors. Okay, based on the basic theorems of the mathematics, we know the eigenvector can always form a set of the basis vectors. So it means that for any n-dimensional vector, we can always express the vector U0 by the linear combinations of all the eigenvectors. We can always do this, and it is the mathematical theory. We can do this, and okay. And right now we know one eigenpair. And after you assume this arbitrary vector U0, and we can try to eliminate the component vectors come from the x1, since we know the x1 already. Okay, so after we assume the U0, so it means that we know all the elements in the U0. Then it is not difficult to calculate the x1 transpose B U0. Okay, since we know the A matrix, also we know the x1 vector, also we know the x1 vector. So we can calculate the x1 transpose B U0. It's B U0. And if we replace the U0 by the following equations, so it will be the okay. Then we, by the theorem, we can get the results like this one. And also remember the eigenvectors, they are orthogonal to both A matrix and the B matrix. So we know this term must be equal to 0. Okay. So on the right hand side, the results of this one should be this. So we can calculate the alpha 1. Then it means that we can calculate the alpha 1. The alpha 1 will be this one. If you have done the normalization of the eigenvector, then if we do the normalizations for the x1, then we will require the x1 will make this value equal to 1. Okay, but I will still write this formula. So even you didn't do the normalizations, you can still use this formula to get the u alpha 1. Okay, so we can get another vector which is called the u0 prime. Okay, and u0 vector is the initial vectors the program user can assign arbitrary vector to the u0. And we know the x1, so we can calculate the alpha 1. So if we use calculate the u0 minus alpha 1 x1, then we will get the vectors like this one. Okay, so you can say the u0 prime vector. The u0 prime vector, which is a vector without the contribution from the x1. So the u0 prime is contains only the contributions from the x2 until the xn. Okay, so that's the first thing we need to do. After you assume the arbitrary initial vector u0, then you need to calculate the alpha 1, and then you can calculate the u0 prime. The u0 prime is the u0 vector take out the alpha 1 times x1. Okay, so we can cover this one. Okay. But remember, all the numerical methods always got some numerical errors. So you should expect we could have some even for the x1 vector or the lambda 1. The first eigenpair we solve, we still could have some errors. Okay, after you got the U0 prime, then you will continue the similar solution procedure for the to get the first eigenpair. Then you will calculate the U1 vector, which is the A inverse B U0 prime. Okay, so you just calculate the A0B U0 prime, and remember this formula will be the okay, so we can calculate the expression for the U1 will be something like this one. And remember for the A inverse BX2, since we know this is the basic formula for the eigenvalue problem. So the A inverse of this one will be the lambda 2 x2. And this one will be the lambda 3 x3. And the next one lambda n x3. Okay, so we can take out the lambda 2. Okay, so then after the calculations, the U1 will be this vector. Okay, okay. I will take a break here, and I will continue to the next hour.